Hello everyone, and thank you for attending my lecture today. In this lecture, I'll discuss what statistical methods in the regression models are designed to do, and I'll show how to carry out regression analysis using the statistical methods and how to interpret the results obtained. I'll provide some graphical intuition in order to gain a little insight into where the statistical methods results come from. So the outline is as follows. We're going to look at some preliminaries, the statistical aspects of the regressions. I'll show how we test hypotheses and some examples how to calculate the beta 0 and beta 1 by hand. I'm going to start with some statistical notations in order to make sure that we are all aware of this. In statistics, we define the population as a set of all elements that are of interest for the statistical analysis, and normally we denote this by N, capital N, which is the population size. And we define the sample as a finite subset of these observations drawn from the population, or simply a random sample of the population, and we use a small n for the sample size. Some other notations that you might see during my lecture notes, we use this E brackets X as an expectation, or this is the expected value of a random variable X. And when we see the next notation, this is gonna be conditional expectation. So we have expected value of a random variable y given, in this case, x given y. Normally it's the other way around. The expected value of y given x. Var of x is the variance of the random variable x. Covariance of xy is the covariance of these two random variables. We saw last lecture how we denote the mean, which is the sample mean, and I give some simple example, which is how we calculate the mean given three random variables. We take the sum of these variables over the total number of the sample, which in this case is 3. So the mean of this example is 5.3. The median, we use this notation, which is the middle value of a random variable x, and we sometimes going to use the summation operator, which is the sum of all values in a range of series of some samples. So the sum of xi and I from 1 to 4 can be expressed in this way. So we emphasize that this alpha and beta, the intercept and the slope, are known true coefficients, while the alpha hat and beta hat are merely estimates, and certainly they're not precise and not the same as the true parameters. That's why we introduce the L term into the regression model. And this leads us to ask whether we are confident how accurate these estimates are. Fortunately, we can test this by using some statistical techniques that I'm going to discuss today. In particular, these techniques enable us to provide confidence intervals and enable us to carry out hypothesis testing on the regression coefficients. So one way to look at this, and I'm going to start with the main issue, is what factors affect accuracy of the ordinary square estimates, and I'm going to provide you some examples by the next graph. If we consider fitting a line through the XY plots in the next figures that I'm going to show you, and these figures contain artificially generated 4 different data set for x and y from the regression model, where we just set up alpha to be 0 and beta equal to 1. So we try to obtain alpha hat and beta hat, so the estimated, the fitted value, that's going to be equal to 0 and 1. So we try to get as much close to the true parameters as we can. So fitting the straight line as the ordinal least square does to this XY plots, we would not expect that all of these lines are going to be equally accurate. So we're going to ask ourselves how confident are going to be about how accurate this straight line going to fit all these points. So let me show you the examples. So if we see in this graph, we have a small number of data points n is equal to 5. So we are not confident, we are less confident about accuracy of the best fitting straight line through all these points. However, if we look at the next figure, figure 5.2, where we have a large number of data points, but they're very scattered, here we have a large variance of errors. We are more we still are not feeling confident because of this large variation in these error terms. In the next figure, we have again large number of data points and they're not so scattered. So we see there's a small variance of the error terms and we are more confident to fit the straight line here. This straight line which gonna fit the XY, gonna leaves out, and we are more confident to fit the straight line here rather than the previous figures. So we are less confident to about the accuracy of the best fitting straight line that we want to draw in our figures here or here. However, we are more confident to draw this straight line having large number of data points. We could have this case where again we have large number of data points, but they're close to near one value of x. So still we are less confident to fit our straight line over here. This leads us to summarize these figures illustrate the three main factors that affect accuracy of the ordinary least square estimates and the uncertainty that surrounds our knowledge of what the variance of beta really is. So the first, we can say that having more data points improve accuracy of the estimation, and this can be seen by comparing figure 5.1 and figure 5.3. So what I highlight here, we have large number of data points and they are less scattered. This brings us to the second condition for the accuracy, and this is the having small errors. This improves accuracy of the estimation. And number three, having a large spread of the values of the explanatory variables is going to improve the accuracy of the estimations. So, to sum up, large number of data points, less scattering or less variability in the error terms, and more variability in X, going to bring us a more accurate estimates. The influence of these factors is intuitively reasonable. With regards to the first two factors, it is plausible that having either more data or small errors should increase the accuracy of the estimations. Probably the third factor is perhaps less intuitive, but a simple example should help you to understand this. Let's suppose we're trying to investigate the effect of education on income, so we use the simple, we write our regression model in this way, and where X is the years of schooling and income people receive, denoted by is our dependent variable Y. So to understand the nature of this relationship, we want to go out and interview all types of people. People with no qualifications, people with secondary school education, people with some post-secondary vocational training, people with university and people with PhD degrees. In other words, we want to interview a broad spectrum of population in order to capture as many of these different education levels as possible. Or in statistical jargon, this means that we want X to have a high variance. If you don't follow this strategy, for example, we interview only those people who have PhDs, we will get a very unreliable picture of the effect of education on income. And in this case, you would not know whether the relationship between education and income was positive. For instance, without collecting data on people who quit schooling at the age of 16, you would not know for sure that they're making less income than those of PhD. So to sum up, this basically relates to the last condition for accuracy of the estimates, which is more variability in X, and this brings us more accurate estimates. So, and this again. The three main factors that improve accuracy of the ordinary square estimates and that I want you to understand today is first having more data points, having smaller error terms, and having large spread of the values of exponential variables. So all these three factors are reflected in a commonly used interval estimates of beta, which we call confidence intervals. What are the confidence intervals? So all this uncertainty about the accuracy of the estimated beta that I talked today can be summarized in this term that we call confidence interval. Confidence intervals is a range that contains beta, the true value of the slope coefficient with a specific probability. If the 95 confidence intervals for beta was, for example, between 3 and 5, this means that if you draw repeated samples and estimate the XY relationship, 95% of the time the true value of beta would be between 3 and 5. Or we are 95 confident that our beta lies in that interval. Confidence level can be either 90%, 95, or 99%, and we usually use 95% confidence interval. If the confidence interval is small, it indicates more accurate estimates, and conversely, a large confidence interval indicates great uncertainty over the beta's true value. Most of the nowadays softwares calculate this confidence interval straight for you, so you don't need to worry about the formulas. But I'm gonna provide you with the formula that you need to be used in order to calculate this confidence interval. So the mathematical formula for confidence intervals is given by this, where you know what is beta hat. This is your estimated coefficient. C is something that is a value taken from the stats table for the student T distributions, and I'm gonna give you more discussion about it in the next slide. And this SB or relates to the standard deviation for our beta, or the standard errors of our beta. An equivalent way to expressing this is to say that there is a high level of confidence that the true beta gonna be something between these two, between the something we call the lower and the upper confidence intervals. So the lower confidence intervals is calculated by taking beta hat minus t times standard error of this beta, and the upper is beta hat plus t critical value plus, times standard error of the estimated beta. These figures provide some example what exactly the confidence interval means. So this is based on a public-private wage gap estimates in UK, and the point shows the estimated mean, and the line shows the 95 confidence interval around this mean. This is just an example to provide you with an insight what exactly we mean by confidence intervals. So we can see, for example, for females in Northern Ireland, that right end figures, the confidence intervals are pretty large, which gonna signal us for the less accurate point estimate for this regions. So all these point estimates are the mean of the public minus private wage differential in specific regions. And these are based on the ordinary square regression estimates, and I control for many characteristics such as age, qualification, marital status, white ethnicity, managerial responsibilities, and so on. This is just an example for you to understand how we can use these confidence intervals in the practice. I can give you an example, and this is the example based on the last time I started with this example. If we want to look at the regression between the house prices and lot size, so this data given here we have a we have houses. We're using data on 546 houses sold in Windsor, Canada, and we want to run a regression of Y, which is the sales price of a house, determined by X, lot size. So the simple way I'm gonna demonstrate you this how we can do it. My data are in Excel, so I can simply copy this data and bring this data in data because I haven't prepared data for a purpose, just to demonstrate we can do this in data. So we can the data and send this data straight to the data software. For those that need data, please send me an email. I can distribute the software for you so you can practice this and see how basically it works. So we copy the variables that we need. This data contains more variables, but at the moment, I focus mainly on two variables. So copy this. I open data, and there is an option that calls data editor. This is one way to do this, and I can paste my data over here. The data gonna ask me the first row should the first row contain the value or the variable names. I'm gonna say the variable names, and these are my data. So I have number of houses in the first column, price of the sale prices, and the lot size, which determines the sale price. So what I want to run is a simple regression model. So remember, I provide you with the command. It's just a simple reg command, and we use my Y is house prices. So house prices is this one. And then lot size is this one, is my X. Lot size determines sales prices. So I run, and this is the output of my regression model. So the ordinary least square estimates the marginal effect of X on Y, and in this case we see the beta hat, our coefficient, the estimated coefficient is 6.59. So this means that increasing lot size by an extra square foot is associated with an average $6.5 increase in the house price. What I want to focus your attention here is the confidence interval that I was talking about. So you can see that data provides me with the 95 confidence intervals, and for my beta, and this is something between 5.72 and 7.47. So we can say that we are 95 confident that the marginal effect of the lot size on house price is at least $5.7 and at most $7.4 per square foot increase. This is something that I show you the formula in our slides, and this is the confidence interval that determines how accurate is our estimate. Um, to obtain the T critical, we only need the significance level and the degree of freedom. What is the degree of freedom? This is terminology I haven't introduced. It's something. This is the number of the values in the final calculations that are free to vary. It refers to the number of independent variables in a set of data that are free to vary. So the critical value for um, T critical is for the two slide t-tests with 5% significance level and 544 degrees of freedom. So the formula for the degrees of freedom is n minus k minus 1, where n is my sample size, k is the number of parameters being used in the regression, minus 1, we normally leave it for the intercept. So why we have in this example degree of freedom 544? Because, as I said, we have number of observations in our estimate is 546. So we have one parameter, the 1x introduced into the estimate. So we deduct this, we subtract this, and minus, so k is 1, and minus 1 gonna bring us 544 degrees of freedom. To calculate the lower interval, we use the formula that I just introduced up here. So this is the formula for the lower interval, and we just gonna use what we got after our estimated beta. So for beta hat, we got 6.59877. Let me go back to the data. This is my coefficient that I get from the estimated coefficient. This is the lot size beta hat. And then I have this 1.96 is the critical T statistic that is for the two-slighted t-test with the 5% significance level. This is given for you. So normally, you know, this is as a rule. I'll bring this rule later on. But this is as a rule, we use this of 1.96. And then the standard error for this beta, we saw after estimating our coefficient is 0.445 something. So we just substitute this here, and we get for the lower end of the interval 5.724. In a similar way, we calculate the upper end of the interval as 7.47. Let me check whether our calculations are correct. If they are correct, they should come here. So we can see that for the lower interval, if you look at the 95 confidence interval, this output is exactly mapped with what we calculated by hand. This is another example which is based on different data set where we have forest loss square kilometers is our dependent variable, and this determines the population density, and this is the output of the regression given below. So what we can see based on this coefficient is that we are 95% certain. We focus mainly on the confidence interval interpretation at the moment. So we are 95% certain that the marginal effect of population density on deforestation is greater than 0.0607 and less than 0.1071. Or in 95 out of 10 cases, intervals like this, our beta is going to be true. So our beta is something between this interval given in red. For the population density. So this is one way to interpret the coefficients, but a more simple way, which I'm gonna give you more insight, is just to look at the p-values The p-values are given in your output after the t-statistic, and this output provides you with the coefficient estimates, the standard errors, t-statistics, and p-value. So a simple way to identify the significance of your estimated beta is to look at the p-value, and we always compare with the critical p-values at 5%, at 1%, 5%, or 10% significance level. So this is your choice as a researcher. You decide whether you compare your coefficient at a specific significance level. So, for example, in this case, my p-value is 0, and I would conclude that my coefficient is highly significant because the p-value is lower at 1% level, it's lower even it's lower at 5% and 10% significance level. So higher than 10%, higher than 0.10 indicates insignificant estimates. So the p-value basically for each term tests the null hypothesis that the coefficient is equal to 0 or that there is no effect. And there's another term that I just mentioned is the standard deviation or standard errors, which again are a measure of the accuracy of the estimated coefficient, and they are also provided in your output over here. So the smaller the standard errors, the better it's going to be your estimated model. But let me focus how we test these estimates. So it is hypothesis testing is commonly carried out by the empirical economics, and because the R square is well given in this model, it gives an overall measure of the goodness of fit of the regression to the sample data. It does not tell us which basically explanationary variable individually is significant. That's why we need to test this, we need to examine this, we need to test whether the coefficients attached to those variables are statistically different from 0 using the test of significance or t-test approach. So the purpose is to answer the question, does the explanationary variable have an effect on the dependent variable? In my example, I want to say whether this lot size has an effect on the price, on the sales prices. So to determine this, we test the hypothesis. We define the null hypothesis and alternative hypothesis. So the null hypothesis, which defines beta equal to 0, states that beta is statistically insignificant or not different from 0. Therefore, it indicates that x, or our explorationary variable, has an insignificant effect on y. The alternative hypothesis, defined as beta not equal to 0, states that beta is statistically significant and different from 0. Therefore, it indicates that x has a statistical significant effect on y. So, in statistics, when we reject the null hypothesis, we actually say that our findings is statistically significant. So by rejecting this null hypothesis, I will conclude for sure that my estimates are statistically significant. On the other hand, when we do not reject the null, we say that our findings is not statistically significant. The way we test hypotheses for certain problems can be approached by the two methods, test of significance approach and confidence interval approach. So I already somehow introduced you the confidence interval approach, but the key idea here, once we talk about the test of significance approach, is that the estimator and the sampling distribution, we look at the estimator and the sampling distribution of this statistics under the null hypothesis. And we need this tabulated distribution with which to compare the estimated test statistics, and all the textbooks provided this statistics, so you can refer to them. The test statistics derived in this way can be shown to follow the t-distribution which looks like this, with the t minus 2 degrees of freedom. So the t distribution is a probability distribution that is used to estimate the population parameters, and it follows a normal distribution. We can see, and especially as long as the sample size is sufficiently large. This is just show you how does the t distribution look like. Uh, so as I said, with the test of significance approach, we need to choose a significance level for alpha, and this also sometimes called the size of the test, and it determines the region where we will reject or not reject the null hypothesis that we're testing. It is conventional to use the significance level at 5%, 10%, and 1% is also commonly used. So if you choose the confidence interval approach to hypothesis testing, then the level of the significance is the 100% minus the confidence level we are choosing. What does this mean? If we imagine the rejection and non-rejection region of this as of the two-sided test, it looks like this. So if we choose the confidence interval and we imagine that the whole area is 100, so the level of significance is going to be 100 minus the confidence level we are choosing. For example, we choose the 5 confidence interval, then 100 minus 5 is going to be 95% non-rejection region. So there are two ways to conduct. I'm going to give you some practical advice how you conduct the hypothesis testing. To test the null or alternative hypothesis, we can look at the confidence interval and check whether it contains a zero. So it's very straightforward and simple, intuitive way. If the confidence interval contains zero, you either accept the null and reject the alternative, and we conclude that x, the exponential variable, has no significant exponential power for y, or our beta is statistically insignificant. This is the case if the confidence interval contains zero. In our example, we don't see that the confidence interval contains any zero. So then we go to the second definition. If the confidence interval does not contain zero, you reject the null and accept the alternative. So we conclude that x has significant exponential power of y, or beta is statistically significant. So this is what we can conclude based on our confidence interval. We can see our confidence interval is between 5 and 7. It does not contain zero. So then we can reject the null and we can accept the alternative hypothesis and conclude that the lot size has an effect on the sales prices. The other way, we may check the p-value, as I said, the p-value for the significance of the coefficient. So useful intuition is to interpret the p-value as a measure of probability that the beta is equal to zero. If we take the 5% significance level, and as I said, this is you as a researcher determine at what significance level you want to reject your hypothesis that you're testing. So if we take the 5% significance level, and if my p-value is less than 5%, so p is less than 5%, then we conclude that beta is not equal to zero, or our x or our exponential variable is statistically significant in explaining why. His beta is significant. However, if the p-value is greater than 5%, p greater than 0.05, we conclude that beta is equal to zero, so beta is not significant in explaining our case. In this, we can see, as I defined, p-value is 0.0, which is strictly less than 0.05, so we can conclude that beta is statistically significant and explaining why. I give you another example. For example, we want to interpret the p-value of 0.03. We can see that p-value of 0.03 is less than 0.05. Then the x variable is statistically significant at 5% level, and then we reject the null hypothesis. However, this is not significant at 1% level because 0.03 is greater than 0.01. So in this case, we reject the null hypothesis at 5% level, but we do not reject at 1% level. This might be the case in a practice. In the example with the regression with the deforestation population density, if we do the same as here, in the same regression as I show you with the lot size example, we get a confidence interval for beta something between 0.0607 and 0.10. So the confidence intervals, first, if we choose to reject by having the confidence interval procedure, the confidence interval does not contain 0, so we can conclude that beta is not equal to 0, or we're accepting the alternative hypothesis or rejecting the null hypothesis at the 5% significance level. Alternatively, we can look at the p-value, which is very small, is 0. To the power of 10, which is less than 0.01. Therefore, we can conclude that beta is significant at the 1% significance level. So it's a highly significant beta, and we can choose both of either of these confidence intervals or p-value procedure to test our hypothesis. In the jargon, in statistical jargon, when the coefficient of the population density is significantly different from 0, we can say it in this way rather than just rejecting or accepting the null hypothesis, or the population density has statistically significant explanatory power for deforestation. This all applies to the same things that we found significant estimated beta. The hypothesis that beta equals to 0 can be rejected at the 1% significance level. Another way for the test statistic for testing this beta is to carry out hypothesis testing is to calculate the t-test. In the case of testing if beta is equal to 0, we use the formula for the test statistic, which is given as the ratio of my beta hat of the estimated beta over the standard error. So the large value of t, large in the absolute sense, indicates that beta is not equal to 0, or while the small values of t statistic indicate that beta is equal to 0. Mathematical intuition for the preceding sentence is given is that beta hat is large relative to the standard deviation. Then we can conclude that beta is significantly different from 0. So the question arises as to what we really mean by the large and the small t-statistic here. In a formal statistical sense, the t-statistic is large or small relative to the critical value taken from the statistical tables of the student t distributions. So for this example here, as a rule, we can use that if the t-statistic is greater than 1.96 in absolute value, then we reject the hypothesis that beta is equal to 0 at the 5% significance level. But if the t-statistic is less than 1.97 in absolute value, then we accept the hypothesis that beta is equal to 0 at the 5% significance level. So in this case, again, what is this t-statistic? This is the t-statistic that you can see here in my example. It's 14.8, and this statistic is significantly higher than the 5% critical level. So of course, I would conclude that my beta hat is statistically significant. And the final statistics that I'm going to introduce and talk today, this is the F statistics. And the F statistic is used to test whether the R square is equal to zero or whether the model has any exponential power. Which I just want to note you that in the simple regression model like this, R square is equal to zero and beta equal to zero are the same things. But once we start talking in a multiple regression model, they will be different. So I'm gonna highlight one with an example next time once we start talking about the multiple regression model, because at the moment we just have a simple bivariate regression model and we have only one x over here. The formula for the F statistic is given as this. So normally the F statistics models of the software, even if you run the simple regression in Excel or in data as I did here, the F statistics, the software calculates for you automatically the F statistics, and in this case is 290.06. But the formula to calculate this by hand is given as this. We can interpret the significance of the F statistics as the same way as the p-value for the R square. So if significance of this is less than 5%, we can conclude that the R square is not equal to zero, or we can reject the null hypothesis. If significance of this F statistics is greater than 5%, we conclude that R square is equal to zero, or we reject the alternative hypothesis. In the example here, we have the probability of a statistic is zero. So again, following the p-value method, we can conclude that it's highly significant, and we can conclude that R square is not equal to zero, or we reject the null hypothesis. In the next slides, I provide you with an example how we can calculate this betas, how we can calculate this beta, the intercept and the slope of our regression model by hand. Although I'm pretty sure that no one does this today, but it's very good intuition for you to understand the methodology. Let's assume I give you an example. Looking at the link between the final mark and lecture attendance. So the link between the final mark achieved on introductory econometrics module and the percentage of lecture attended for students in the course. We have a sample of 20 students, and the data given in the next slide is this one. So the data collected give the student final mark in percentage and the percentage of lecture attendance. It ranges from 0 to 100. So we can see the higher is the attendance, about 90%, the higher is going to be final exam mark. So we want to link this. We want to see whether the X explain Y in this model. However, we do this by using the formulas and calculating this by hand. The econometrician proposed to were proposed to estimate the following linear regression model: Y equal to beta 0, beta plus beta 1 X, and in arrow term. So Xi in this example is my attendance, lecture attendance in percentage. So, and Y is the individual student's final percentage mark, and X is the percentage of lecture attendance. We define the error term as the disturbance term that has the normal properties associated with the classical linear regression model, normal distribution, the conditional expectation of error term equal to 0, and so on. So we try to find the least square estimators for the intercept, the beta 0, and for the slope beta 1. The method of ordinary least square estimates that I talked about in the last class. Choose the values of this beta 0 and beta 1 that minimize the regression sum of square. You remember I showed you some graphs, the fitted value that tries to fit the data point as close as possible, and this minimize the residual sum of squares. So the formula that we use was given as the sum of the square error terms, defined as the sum of y minus beta 0 hat minus beta 1 hat times xy to the power of 2. And we derive, actually I'm not showing the derivation of beta 1 hat and beta 0 hat, but these are the formulas that we can use to calculate by hand our estimated coefficients. So where the y bar and x bar are the means of this, and the latter expression is useful to calculate the betas by hand. So having this, we can easily calculate the terms that we need and to define in these tables. So we take the multiplication, we take the x times y and calculate the x squared term and y squared term because we're going to need it for our formulas over here. And then we just substitute for the we substitute in our formulas in order to calculate our beta 1 hat and beta 0 hat. So we first calculate the means, which is equal to the sum of all elements in y over the sample size. So it's equal to the ratio of 1,153 over the 20, and the same for the x. And this gonna brings us to this regression equation. So for the slope parameter, we have 0.72, or for the intercept we receive 11.1. So which means for the slope parameter, for 1 unit increase in x, the dependent variable increased by 0.72, or for 1 percentage point increase in attendance, the average module mark is predicted to increase by 0.72 percentage points. And the intercept, which means that the average module mark is predicted to be 11.1, or 2 decimal place when there is 0 attendance. So this is the lecture today, and overall we discussed how to check the accuracy of the estimate and what the confidence intervals is, how to test our hypothesis, and how to look at the p-value and the confidence intervals in order to interpret our betas. Thank you so much for attending the lecture. If you have some questions, please don't hesitate to drop me an email.